The last type of the temperature sensors we will discuss in this course is fiber optic temperature sensors. This type of temperature sensing is based on an interesting method. And as you can see in the simplest structure, we have two path of fiber. The first one is for transmit light, and the second one is to receive light. We transmit the light to a specific end, prism shape end, as you can see. The sensor, the main part of the sensor, this prism shape part of the sensor is the main part of the sensor. It consists of gallium arsenic semiconductor temperature probe, and this single crystal gallium arsenic is epoxied at the end of two side-by-side optical fibers and acts like a mirror. As you can see, the light will be passed through the sensor, and based on the temperature in the environment, the transmitted light will be the intensity of the transmitted light will be changed. These sensors can be quite small, compatible with biological implantation. After being sheeted, good sheeted, we need a good sheeting isolation, and because of maybe biocompatibility problems. And one fiber transmits light from a light emitting diode source to the sensor, where it is passed through the gallium arsenic and collected by the other fiber for detection in the readout instrument. Note that some of the optical power traveling through the semiconductor is absorbed by the process of rising valence band electrons across the forbidden energy gap into the conditioned band. Because the forbidden energy gap is a sensitive function of the material's temperature, the amount of power absorbed increases with temperature. It means that more temperature, more absorbance of the power of the light. This type of sensor is suited for temperature measurement in the strong electromagnetic heating field and also in MRI systems, because we don't have any metal parts in this type of sensor. Okay. The next subject we will consider in the following is optical measurements. We use optical measurements in maybe almost all of the clinical chemistry lab instruments. Analyze samples of blood and tissue removed from the body, measure the oxygen saturation of hemoglobin, and to measure cardiac output. Usual optical instrument has a source, filter, and detector. As you can see, we have a source here, a filter, and a detector. These three parts of this type of measurement is the main parts of the system, and a common arrangement of component is like this. We have a source of light, we have some filters to filter and select the specific light band, wavelength band. The sample placed inside this cuvette, and the past radiation, the past light will be collected by these lens and focus on the photo tube. Nowadays we have some solid state systems like this, which is fabricated for some specific objectives. We have light emitting diode inside it, and also a photo transmitter and some lenses to collimate it and collected it, and also the cuvette um, hole to place the cuvette inside the solid state uh, detector. As I mentioned before, we have some light source in optical instrumentation. The most commonly used source of radiation is tungsten lamps. Radiant output varies with temperature and wavelength as given by this equation we discussed before. And we know based on this equation we mentioned before, for higher temperature, lambda m, the maximal wavelength of the radiant output curves shift to a shorter wavelength. It means that low temperatures then yield a reddish color in infrared lamps, whereas high temperature yield a bluish color in photofluid lamps. The total radiant power Vt can be found by that equation. Vt equals epsilon sigma T power 4. Uh, and also, this statement is important also. Filaments are usually coiled to increase their emissivity and efficiency. We use coiled filaments because we want to increase the emissivity and efficiency. For using instruments, short linear coils may be arranged within a compact, nearly a squared area lying in a single plane. Light amplification by a stimulated emission of radiation or laser is another important radiation source which we'll discuss in this course in brief also. We will discuss about the types and the color of laser sources in the next slides. Each word in this term is important. Light. We are talking about light. Amplification. We are talking about amplification of light by a stimulation, emission of radiation. We have some radiation from emission, which emission? A stimulated emission. We have some materials can generate laser, but at the first time before a stimulation, this material cannot emit any radiation because the population of the excited atoms is low, is small. After a stimulation, we have an inverse population, and the stimulated and excited atoms will be higher than the non-excited, non-stimulated atoms. This situation will be occur using a simple light source, for example, a PN junction light source, a, polished area acts like a mirror, and the feedback of the um, reflected light inside the chamber will uh, form a resonant optical cavity. Also, simulated emission means that the forward current pump a large population of the molecules to an excited energy level. Radiation incident on the molecules cause the production of additional radiation that is identical in character. Laser output is highly monochromatic, collimated means parallel, and phase coherent. Phase coherent is important because a simple light source, for example, a white simple light source, is non-coherent, has non-coherent output. Therefore, the output rays will be scattered in the space. But because of the phase coherency in the output of the laser sources, we have highly monochromatic, highly collimated, and phase coherent output. We should emphasize that PN junction lasers are not widely used because they operate in the infrared and require current densities of 1000 ampere 2 centimeter square or more. In the previous slides, we talked about fiber optics, and now we want to explain the geometrical structure of the also the radiation path inside a fiber optic. Fiber optics are an efficient way of transmitting radiation from one point to another. We have two main parts: transparent glass or plastic fiber here, with a refractive index N1, is coated or surrounded by a second material of a lower refractive index N2. N1 is larger than N2, therefore. Based on Snell's law, if a ray, a beam, enter to a second material, the angle between the angle of the incident and transmitter beam can be calculated by the Snell's law. As you can see, where theta is the angle of incident shown in this figure. As I told you before, N1 is larger than N2. Because N1 is larger than N2, therefore the angle inside region N2 will be larger than the angle inside N1, as you can see. Here N1 and here N2, we have a borderline here, and theta 1 and theta 2, as you can see here, because N1 is larger than N2, I rewrite it, N1 sine theta 1 equals N2 sine theta 2, and because N1 is larger than N2, therefore theta 2 will be larger than theta 1. If I increase theta 1, also with increasing the outer theta 3, theta 4, we can find a critical point. We called it ICC, mentions to the critical. We can find a point that in that point theta 2 equals to 19 degree, and therefore the sine of 19 degree will be 1. It means that theta 2 wants to be 90. But the light cannot be travel on the border, and the ray of light is internally reflected instead of travel on the border. In this situation, the border acts like a mirror. Before that critical point, the ray will be enter to the coating with index of N2. But at this point, and after that, larger angle of theta IC, the ray will be reflected inside N1 and will be remain in this main fiber part. And now you can see that the ray start to travel inside fiber instead of leave the fiber. Before this theta, before this critical theta, critical angle, as you can see in theta 2, the ray enter the second material, the coating, and wants to leave the main core of the fiber. But for the larger angles of theta IC, larger angles than theta IC, the ray will be remain in the N1 in the main part of the fiber and will not leave and will travel forward. To calculate this critical angle, you can use this equation. It's so simple. When your theta is 19, this is 1, therefore theta 1 can be calculated from two refractive index N1 and N2. Rays entering the end of the fiber at larger than, and also we should talk about the outer angle. We have a fiber, okay? We have a fiber, and this fiber has an entrance point, an entrance terminal. We have a fiber, something like this, and I should irradiate the ray in a specific angle. The angle here, for example, theta 4 or theta 3, should be provide the correct internal reflection angle. Therefore, we should select a small theta 3, a correct theta 3 or smaller than that angle to achieve the correct theta IC or larger angles. Larger angles of theta I prime is larger than theta IC. Therefore, for example, theta 3 prime will be smaller than theta 3. We should determine these values because if I choose large angles for entrance, for example theta 4, the light will be pass through the coating and is not able to travel inside N1 and will not transmit by the fiber. We can call it they escape through the walls. They escape, run out of the fiber. And also, if I choose so small angles, so small, the angle theta 1 prime will be larger than normal and the steps will be larger than normal and it leads to bad transmittance of the transmission of the rays inside the fiber. Therefore, we should choose not large and also not low angle. It is a trade-off between escape through the walls and good traveling of the ray inside the fiber. Fiber optic sensors are replacing some conventional sensors for measuring a variety of electronic, mechanical, pneumatic, and hydraulic variables. We have two types of fiber bundles. The first one is non-coherent fiber bundles called light guides. If we have a fiber with no correlation between a fiber's spatial position at the input and the output, as you can see, we have some non-arranged, not correlated. We don't know the position of this fiber at the second end. Therefore, this fiber cannot transmit image, because for image transmittance, for image transmitting, we should use a coherent fiber bundles. We should use a coherent fiber bundles. The fibers occupy the same relative position at both end face, and now you can transmit image. If you want to transmit, for example, an image with non-coherent, you cannot achieve a meaningful image at the output, because the location of pixels will not transmit at the correct location at the second end. But using the coherent fiber bundles leads to a correct transmission of image from the one side to another side. An image at one end is faithfully transmitted to the other end.